Hello and welcome everybody to lesson number 3 titled SHM and Graphs. I'm coming to you today in, this is what I wore to my wedding. This is my wedding dress. It still fits me, so I guess I'm doing a good job of watching my figure. But without further ado, let's get started with just the intro problem today. So we're just going over the graphs for simple harmonic motion, how they relate. And we'll also talk a little bit about energy. But I know we haven't talked about energy specifically with simple harmonic motion. We're kind of weaving it in with graphs, but since we just came out of the energy unit, I hope that it'll make a little bit more sense as we, or that it'll be a little bit easier and you'll pick it up quickly. I'm pretty confident of that. So now let's get started with the intro. So the intro problem says, the position versus time graph below shows a spring oscillating horizontally in SHM. Label the indicated locations on the graph with the corresponding location ABC on the diagram. And then it says assume that the right is the positive direction, like we usually do. So I'm going to draw out these graphs real quick so that we have them as a reference on the sheet, since I am just working from the whiteboard. I'm not going to label the axes, I'm just going to draw the shape right here. Then we've got a line down here, a line in the middle, a line at the top. And so we've got that graph, but then we've also got the little spring diagram right here with position A, position B, which has that unstretched spring length line right here, and position C. All right. So what we're supposed to do is we're supposed to take those A, B, and C's and put them in the blanks in the right order. So we're trying to figure out which position of the spring corresponds to which point on the graph. The important note here is that it says that right is the positive direction. So we've got the axis, there's a positive side, the top up here, and then the negative side, which would be the bottom, obviously. And so you see the graph is going from a positive position, a really high positive position, down to a really low negative position, and it's bouncing back and forth between that. Just like the graph or the spring itself is bouncing back and forth between a far left position and a far right position. So I think it might be clear that the far left position and the far right position correspond in some way to the far bottom position on the graph and the far top position on the graph, right? And so the key here is in the question. It says that the right is the positive direction. So we have the C, point C is all the way to the right, as far right as we'll go. So it corresponds to the far positive point, right? So this C goes here in this top point because it's the positive direction. It's the furthest in the positive direction. Right is positive. So it goes up there. And it might not be too surprising, right, that we've got that point in the middle. B is in the middle at that unstretched length, right? So it makes sense for it to be at that x equals 0 along the x-axis, right? B goes there, and that leaves us with A, obviously, down here at the bottom. But if left is the negative direction, it makes sense for A to be the full negative position, right? So yeah, I think that's pretty straightforward, right? Right in here is positive, C is far right, C is far positive, and then it follows from the rest of that. So I hope that's pretty clear, but if not, we will continue to see examples with it, and I hope it makes more sense. So I'm going to erase this, and we'll move on. So the examples here don't have like problem numbers per se, but there's like sets of questions. So everything on this second page here is like effectively problem 1. It's just parts of the same problem. So let's take a look at problem 1, aka just that set of problems on the first page. So problem 1 says, the motion of a spring oscillator with a 10 kilogram mass is graphed below, and then it gives you the graph. So I'm going to draw that graph right here. I'm going to draw it a little small because there's 3 graphs that we have to draw. Time in seconds. 2, 4, 6, 8. And then it's a sinusoidal graph. We see that it's got a period of 2 seconds, right? Because it takes 2 seconds to do one oscillation. So your graph will look like this. Right here. That positive peak is at 1, and the negatives are at -1, right? Oscillating between 1 and -1. So our first part says to draw the graph of the velocity of the spring on the graph below, and then it gives us a little blank graph to fill in. So I'll draw those axes here too. Velocity and time. Same time scale here, right? 2, 4, 6, 8. So we have to draw the velocity versus time graph given the position graph of the spring. So we kind of have to think about the motion of this is a spring oscillator, it says. Whether it's vertical or horizontal doesn't really matter here. So when the spring is bouncing back and forth like this, right? It's moving this way, it gets stopped for a second, and then it starts moving back the other way, and it stops for a second, right? It's changing directions on those ends, so it has to stop for a second before going the other direction. So at the ends there, at our peak positions on the position graph, this one up here, right? Those are kind of where it's stopping for a second, right, before it changes direction. So at each of those peaks, whether it's the top peaks or the bottom troughs down here, right, that's where it stops for a second. So everywhere there's a peak on the position graph, there needs to be a 0 on the velocity graph, right? 0 velocity at those peaks. So that means we'll have a 0, 0, 1, 2, 3, 4, 5, 6, 7, and 8, right? Because it doesn't matter if it's positive position or the negative position, it stops for a second at each one. So every second we have a stop. So those are where we have to cross through the x-axis and get 0 velocity. But which way do we go? Do we loop up first or do we loop down first? Let's look at the position graph. So we start at +1 here at 0 seconds, and then it starts going from +1 towards -1, right? It goes down towards -1. So it's going from the positive to the negative. So its velocity is in the negative direction, right? Going from positive to negative. So our velocity here at first has to be negative velocity, right? Because it's going towards the negative. And then at 1 is where we hit 0 again. So we have to be in the negative direction here, and then we hit 0 again, right? That's what it says. So, and then we're at -1 here at 1 second, -1 position at 1 second, and then that's where it flips and starts going back towards the positive direction, right? So from 1 to 2, it's going towards the positive direction. So it needs to be a positive velocity. Yeah? And then this is where our graph just repeats, right? It goes back and forth and back and forth. So it shouldn't be too surprising that we just fill it out, and then it looks like this. Just, it's going from positive to negative, negative velocity. It's going from negative to positive, it has to have a positive velocity. Lovely. Our next example is our next problem, I guess, or part of the problem, is for us to draw the kinetic energy of the mass on the end of the spring. So I need another graph here, but for kinetic energy, which is measured in joules by time, 2, 4, 6, 8. So kinetic energy, the energy of motion. Kinetic energy is a function of velocity, right? The way we calculate it, I'll write the formula over here on the side, I guess. Kinetic energy is 1/2 mv squared, right? So it's a function of mass and velocity here. Our mass stays the same because it's the mass on the end of the spring, but the velocity here is what's changing, right? And when you have more velocity, you have more kinetic energy. So it shouldn't be a surprise that wherever we have a maximum velocity, we should have maximum kinetic energy. But notice that it's speed. Remember, whenever we talked about energy, I'd say that negative energy doesn't really have a meaning. You either have energy or you don't. We're not really worried about direction of energy. You have the energy. So energy doesn't care if it's positive or negative. If you look at the formula, the speed here is squared. So if you look at our graph, we have negative values for the velocity and positive values. But the square actually gets rid of that negative sign. So kinetic energy doesn't care if your velocity is negative, it just cares how big the velocity is. So at each of those peaks, whether it's a peak or a trough, we should have a maximum velocity, right? So everywhere you see a peak, you should have a maximum velocity. It doesn't matter if it's positive or negative. So at that's not even 1 second, that's a half a second, right? Everywhere you see a peak, there should be, I'm just lining them up with the peaks, basically. I think there's probably, I should have probably done this the other way, because I think it probably makes more sense the other way. So there should be a peak there. Now, this is the way I probably should have said it first. But everywhere there's zero velocity, there's no kinetic energy, right? So everywhere you have a zero on the velocity graph, you should have a zero on the potential energy graph. So that's at every second, right? 0, 1, 2, 3, 4, 5, 6, 7, and 8 should have a zero because it's got zero speed. If you plug a zero here, you get a zero for the kinetic energy. So we just connect. So your graph looks like this. Notice our little squiggles are a lot closer together here. We have a higher frequency of the squiggles, right, or a lower period of the motion. And so that's because it doesn't care about direction, right? So we had to go back up every time there was a peak, not just when there was a positive one. So I drew mine a little close together, but I hope it looks all right. But yeah, that's the kinetic energy. It doesn't care if it's positive speed or negative speed. That's really the big difference here, why the shape changes. So our last part says, assume the maximum measured velocity is 5 meters per second. Go back and add scales to the graphs above. So you notice that we don't have any scales on our two graphs here for the velocity of the kinetic energy because we didn't have enough information. But now we do. So we have a maximum measured velocity of 5 meters per second. So if we go to the velocity graph, these peaks up here, the maximums are at 5 meters per second. And conversely, if it's going 5 meters per second positive, its maximum in the negative direction would be -5, right? Because it's going back and forth from 0 at the ends. It just is changing direction. So the maximum would also be -5, and the minimum, I guess you could say, is just -5. So it's oscillating between 5 and -5 meters per second. Now we have to figure out kinetic energy. Again, it doesn't care what direction it's at, but it would be our maximum kinetic energy happens at our maximum velocity. So if we take our kinetic energy formula, we can plug in our maximum velocity and find maximum kinetic energy because we're given a mass. So our mass, it says, is 10 kilograms. 1/2 mass is 10 kilograms times our maximum speed squared, which is 5 meters per second. Again, you could plug in -5 here, right? The negatives would cancel out, so it wouldn't matter. So you get 125 joules for maximum kinetic energy, so that goes over here, 125. Boom. And that's all for that problem. Right? I hope that checks out. Erase time. So our second page of examples is fairly similar to the next one with just a little bit of some minor tweaks. So if you'd like to challenge yourself a little bit, because this one, if you look, it has force on there. You can go ahead and try and get a feel for it. If not, that's okay. You can just follow along with me. So the second problem says the motion of a horizontal spring oscillator with a 5 kilogram mass is shown below. And then gives us this graph, so I'll redraw the graph here, the position graph that's given us. Time in seconds. 2, 4, 6, 8. What you should notice here is that we have a longer period, right? It takes 4 seconds to do one full oscillation. So our period here is 4 seconds. And it goes back and forth again, just between 1 and -1 meters. Lovely. So our first one, this is a spring oscillator. Our first graph is the force applied to the mass over time. So I'll copy down those axes, and then we can think about force as measured in newtons. 2, 4, 6, 8. Okay. So we're trying to figure out the shape of our force graph first. So it's going back and forth, right? And it's a spring oscillator. So remember, the restoring force of the spring oscillator is the force of the spring pulling the mass back towards the middle, or pushing it if it's compressed, I guess. The spring applies force in a way we did a lab with this, right? The formula for the way that spring applies force of a spring is equal to K, or the spring constant, times delta x, aka how far you stretched it, right? If you stretch a spring further, it's applying more force. So it shouldn't be surprising then to say that wherever the spring is stretched the most, we should have the most force being applied, and where the spring is not stretched, then we should have the least force being applied. So anywhere that the box is at the middle position, the 0 position, the spring isn't applying any force, right? It's at that unstretched length, that 0 stretch, and so if we plug in a 0 here for delta x, then we should get 0 force. So if we look at our position graph, everywhere there is a 0 on the position graph, there should be a 0 on our force graph, because everywhere it's at the 0 position, the spring is not applying any force. So we have a 0 at 1, a 0 at 3, 5, 7, just to the odd numbers, right? So those are where we should have zeros. And it follows that everywhere it's at a maximum position, we should have maximum force. So we have maximums at 0, 2, 4, 6, 8. But the question is, which one is it? Like at 0 seconds here, is it a positive force maximum or is it a negative one? So let's think about this. Whenever it's stretched in the positive direction, right, it's at point C. I'm going to draw a little picture actually up here beside it. Then, I'll put it up here. Scroll up a little bit. So I'll draw it in the far positive direction because that's where we start at our graph. And so the unstretched length is here. So this was point C, like in the intro. So it's stretched to its far positive position, far to the right. So if we're far to the right, which way is the spring trying to pull the mass? Back towards the equilibrium position, right? So it's the force of the spring is this way, right? Force of the spring. It's trying to pull it back towards the negative direction because that's where the 0 is. So when we're at that positive 1 position, we're far in the positive direction, it's trying to be pulled back in the negative direction. So when we're in the positive position, we're positive to the right, but the force is to the left. So we should have a negative force if we have the positive position. So we should start at a negative maximum right here. And at 2, we're far in the negative direction, which means that the force is pulling us back towards the positive direction. So we should have a positive, and then we just oscillate from there. So connecting the dots, our graph should look like this. Lovely. If we're in the positive direction, the force is trying to pull us back to the negative. I think that makes sense, right? So notice again, if you look ahead, this one doesn't give us that extra piece of information down here at the bottom to go back and do axes. And I don't expect us to do axes here. If we get a certain problem, I won't give you both these steps, but I do want to show you real quick how that would work. So I'm gonna erase this formula to give us some more space. So you actually can, with the information given, figure out the axes or the values to put here on this graph, the maximum force and the negative force. You can figure that out, and I will show you how. So the first day, the first day, we talked about the formulas that you can use to pull information and determine like the period of a spring oscillator, right? And so that formula was period of a spring is 2 pi square root of m over k, right? So based on the information we have that there's a 5 kilogram mass from the problem statement. So we know our mass is 5 kilograms, and if we look at our graph, right, the period is 4 seconds. So we can actually figure out the k value of the spring. So our period is 4 seconds, because it takes 4 seconds to do one oscillation, right, times 2 pi square root. The problem says the mass on the end of the oscillator is 5 kilograms divided by k. So if we do the math there, our k is 12.3 newtons per meter. Now, the formula that I just erased, we have to rewrite it now. We can use this k value to determine the force of the spring, depending on how far it's stretched, right? Force of a spring is equal to k delta x. So we have the k value, and if we're looking for the maximum force, right, we would use the maximum stretch, which is the 1 meters right here, right? That's our maximum position on our position versus time graphs. So 12.3 newtons per meter times our maximum stretch, which is 1 meter, just equals 12.3 newtons. So 12.3 newtons is our maximum force, right? It goes here, and obviously if we plugged in -1 here, we would get -12.3, right? So that would be our maximum position in the negative, our maximum value on the negative side. So it goes down here, right? So yeah, again, that's just kind of like a thing that you could do, pretty cool. But I wouldn't give you both things. You'd either be like figuring out the forces or the graphs. It's not like do all of this in one problem. So don't worry too much about that. But that brings us to the last problem, which it says redraw the position graph as if you pulled the spring back to 0.5 meters initially, and gives you position versus time axes here. X, t in seconds, 2, 4, 6, 8. Great. So we're redrawing the position graph as if you pulled the spring back to 0.5 meters initially. So if we look back at the original position graph, right, we pull it to to just 1 meter and then release, because that's where we start off, right? We start off at 1 and then it goes back and forth. So this time we're only pulling back to 0.5. So we should start up here at positive 0.5. And I mean, from what we see in the graph, obviously it oscillates back and forth between positive 0.5 and negative 0.5, which is already on your graph, it's not on mine. So our negative maximum should be negative 0.5, if that makes sense. But we start off up here, which is why I've got the dot. So you might be thinking, well, where do we go from here? Like where's the next point that we're supposed to go to? Where's the period? So if you think back to well, not yesterday's lesson, but the previous lesson, we looked at what affects the period of motion for a spring oscillator. And specifically, I showed you an example of me changing the distance that I pulled the spring back initially. And if you remember, pulling the spring back to a different distance didn't change the period, right? This was not one of the factors that changed the period. So our period should actually be the same as it was before, which was 4 seconds, right? So it took 4 seconds to do one oscillation, meaning if we start off with a peak up here at 0 seconds, then our next one should be at 4 seconds, right here, with a negative in the middle, right? So it should look like this. So we have the same period effectively as the original graph at the top of the page. It's just lower, right? It's got a smaller height of the peaks, but the period's the same because distance that you stretch the spring doesn't affect the period. Lovely. Give it a moment. Now erase. Lots to erase here. Very physicsy looking problems there with 3 graphs, a diagram, and some problems written on that one, right? Great. Okay, that brings us to our last set of examples, which is, it's a pendulum, but it works pretty much the same. So I would recommend here going back and at least doing the graph parts. You might get a little confused when you get to the bottom with going back and adding the information on the axes, but go ahead and try out the graphs at least. I'll wait. And now I'll go. So I'll read it off. The motion of a pendulum with a 10 kilogram mass is graphed below, and they give us the little graph. Y 2, 4, 6, 8. And this one has back to a period of 2, right? Oscillating between 1 and negative 1, 1, negative 1. Starts off high. Period of 2. 2 seconds. So it looks like that. And our first one again is to draw the velocity graph. And again, it doesn't give us axes because we're going to go back and figure those out. Speed, time in seconds, 2, 4, 6, 8. Okay. Great. So we have to figure out again how the position corresponds to the speed. Now, this, it shouldn't be surprising, is actually really similar to the spring example. So these, again, the peaks here, the tops and the bottoms on the position graph correspond to when the pendulum is at the end. When it swings here, that's either a positive or negative depending on which way is positive, right? It swings out, stops for a moment, and then swings the other way, stops for a moment, swings the other way, stops for a moment, swings the other way. So at each of these peaks, once again, there should be 0 velocity, because that's when it stops and then changes direction. So at 0, at 1, 2, 3, 4, 5, 6, 7, and 8, we should have 0 velocity, much like the spring. And so again, we have to figure out which way is it going, which way is it starting to go from 0 to 1. Now, in this case, again, we start off at +1, and we're going towards -1, meaning we're going in the negative direction. So our velocity is negative. So it starts off negative, exactly like the spring one in this case. So it looks like this, and then from 1 to 2, it's going in the positive direction. From 1 to 2 seconds, it's going in the positive direction. From -1, it's going to +1 on the position. So it should have a positive velocity. And then we just connect. Like this. So our graph actually looks exactly the same as our spring position, or spring velocity graph, rather. And that's because the motion of the basics of the motion is basically the same. It's all simple harmonic motion, so there should be some similarities, basically. Lovely. That brings us to the next one, which is draw the graph of the kinetic energy of the mass on the end of the spring. So another kinetic energy, that should say on the pendulum on mine. I'll change those whenever I upload them for you. So it should say in the end of the pendulum, and hopefully I remember to do that before posting this. If not, you can laugh at me. Graphs, kinetic energy again measured in joules, time in seconds. Same axis here, 2, 4, 6, 8. All right. So again, velocity or kinetic energy is a function of velocity. Wherever you have maximum velocity, you should have maximum kinetic energy. Wherever you have 0 velocity, you should have 0 kinetic energy. So I'm going to go with the zeros first, because I think that's the easier way. I just made the mistake of doing it the other way the last time. So everywhere we have a 0 on the velocity graph, we should have a 0 on the kinetic energy graph, which is at every second mark right here. 0 and 1, 2, 3, 4, 5, 6, 7, and 8. Everywhere there's a 0 here, we have a 0 here. So again, the formula does not care if it's a negative velocity or a positive velocity. We should just have a maximum kinetic energy point wherever we have a peak or a valley. So we have a peak in between 0 and 1, in between 1 and 2, basically just right in between all of these dots, right? Everywhere between the zeros, we have a peak. Like that. Then we connect. Squiggle, 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 squiggle. Boom. Lovely. Great. So that's the shapes of our graphs. And that brings us to the last bit, which is assume the pendulum is pulled back to a height of 0.2 meters above its rest position before being released. Go back and add scales to the graphs above. Okay, so notice that this one gives us a height that it's initially pulled back to, does not give us the velocity. So there's a little bit of an extra step here. I'm going to draw a little diagram, and we can see what's going on here in terms of energy, because this is going to have to be an energy problem. So the pendulum's pulled back up here, and I'll make this our ground and give us a little reference here, right, for its base position down here on the bottom. That's where it would be at rest. So it says it's pulled back to a height of 0.25 above its rest position, meaning this distance right here is 0.25 meters, the height that it's pulled back right there. Okay, so that's how much it's pulled back initially, and then it's released from there. So this actually becomes a little bit of an energy problem. So this is basically, we've looked sort of at a pendulum before, but we looked really a lot at that skateboard in the half pipe. So whatever we can calculate his potential energy at the top, right? And as he goes down the half pipe, or as the pendulum swings down the path, your potential energy up here turns into kinetic energy as you go down, right? So we can use this initial potential energy to figure out kinetic energy. So let's go ahead and calculate that initial potential energy. Remember that gravitational potential energy, PEG, is mgh. So let's look back at the problem if we have mg and h. Yes, we have m, right? It says the initial problem statement says the motion of the pendulum with a 10 kilogram mass is graphed below. So our mass here, m, is 10 kilograms. G, that's just acceleration due to gravity, right? Positive 9.8. And our height is that initial height that we're pulled back to, right? H is 0.25 meters. So we can just plug in 10 kilograms, 9.8 meters per second squared, and a height of 0.25 meters. And if you do just multiplication, if you do that math, you should get 24.5 joules for your potential energy here, initial potential energy, right? But notice that for the graph, we're calculating, or we graphed kinetic energy. So we need to know its maximum kinetic energy in order to put that little mark on the graph. So how do we figure that out from what we have? Well, here I used the reference point, right? The zero potential energy reference point here was its rest position down at the bottom. So at that bottom point, straight up and down, it has zero potential energy is what we said. And we also said that your potential energy here is converting into kinetic energy as it swings, right? So at the point at which you have zero potential energy, all of your potential energy has been converted into kinetic energy, right? So all of those 24.5 joules are now in kinetic energy right here at the bottom. And then it starts going back up and kinetic turns back into potential. But we're concerned about that maximum potential energy here, right here in the middle at the bottom. So it shouldn't be a surprise that if we're ignoring friction and air resistance and all that, that our maximum kinetic is also 24.2 or 0.5 rather, right there at the bottom point, right, where all of our potential has been converted into kinetic. So that right there is our maximum kinetic, meaning it goes here on our graph, 24.5 joules. Lovely. And so now we can use that information to figure out velocity. We're just doing basically in the reverse of the way that we did in the previous problem. So we can figure out maximum velocity using the kinetic energy formula, 1/2 mv squared. So we know our maximum kinetic energy is 24.5. 1/2, our mass is still that 10 kilogram mass, speed squared. And then we just solve for speed, right? That's our maximum speed, because it's our maximum kinetic energy. And so if you do that math, is 2.2 meters per second. That's our maximum velocity. Again, this is maximum velocity. It doesn't, maximum speed actually, really. So it does not care about direction. That means that's positive 2.2 here is the top maximum, and negative 2.2 is the bottom maximum. Boom. So that's the graph. That's the sheet. If it's confusing at all, please let me know. I think there's a good diversity of examples here. So if you rewatch it, I try to be careful with the way I was saying things. Please rewatch if you need to. There's the Google form that you have to fill this out. If you have any questions at any point, message me, let me know. I'm here to help. Carry on with your day.